Hello, and welcome to today's webinar on climate risk analysis using a fully web-enabled GIS. Thank you for joining us today. My colleagues and I will introduce how the ArcGIS ecosystem provides the means for businesses and individuals to understand, mitigate, and respond to climate risk-related risks. As Noelle said earlier, today's webinar will be recorded and made available for future viewings. We will keep you on mute during this session, but we encourage you to drop your questions or comments in the chat at any time throughout the presentation. We will take time at the end to address your questions. We will also take the opportunity to engage with you in 2 polls to understand your interest in this field. Note that all of the examples and use cases discussed throughout the webinar will be provided as resource links in a follow-up email so that you can further enhance your knowledge on climate risk analysis. The potential effects of global climate change include more frequent wildfires, longer periods of drought in some regions, greater floods in others, and increase in the number, duration, and intensity of tropical storms. Last year alone, the cost of natural disasters was nearly twice that of the previous year, jumping from about $116 billion to $210 billion last year, according to a report by global reinsurer Munich Re. The US alone saw losses in the order of $95 billion, with damage from storms, hurricanes, and wildfires contributing the most impact. Combined with NASA's analysis pegging 2020 as the hottest year on record, the numbers are all pointing to accelerating risks due to climate. Such increase in costs caught many companies off guard, although those that had incorporated predictive climate risk analysis into their planning were better prepared and quicker to rebound. Businesses and government leaders who need to understand climate change impacts and mitigate disasters rely on climate risk analytics and location intelligence from Esri. Assessing climate impacts and areas of risk require an interdisciplinary approach that leverages data from demographics, Earth observations, and environmental applications that traditional meteorological analysis packages are just not optimized to handle. GIS technology, however, provides the means to analyze and contextualize data from a multitude of sources and models to identify climate patterns and assess risk. You can think of ArcGIS as a framework for applying science, mapping, and analytics to address climate risk, monitoring, and mitigation strategies. Seen here on this slide are a wide range of use cases and organizations utilizing ArcGIS to address climate risk. For example, NOAA's Climate Prediction Center provides climate forecasts for the nation as well as globally. NASA's Earth Sciences Division supports disaster response. AT&T, in cooperation with Argonne National Laboratory, mapped decades of climate risk using big data and location intelligence to understand infrastructure that may be at risk due to climate change, and then to adapt their business to its impact. Today's webinar is the second in a 5-part series on applied meteorology using ArcGIS. The first webinar, entitled Visualization and Analysis for Meteorology, is now available for viewing. The titles of the subsequent 3 webinars in the series are listed on this slide. This webinar series takes you on a journey to see how ArcGIS advances the understanding of atmosphere to benefit both society and science. We welcome you to join us along this journey, and links to these additional webinars will be provided in a follow-up email. My name is Lorraine. I am the Director of Earth Sciences Solutions here at Esri, focused on geospatial technology for Earth Sciences applications. I'm joined today by Jeff Donzie, who leads our weather and climate community efforts, as well as manage our relationship with the NOAA National Weather Service. We have Lou Zhang, an Esri solution engineer supporting multidimensional data analysis with a concentration in data science computing, and also James Sill, a senior Esri solution engineer with extensive background on Earth systems applications. Our agenda includes brief presentations and demonstrations on the tools, workflows, and resources that have been developed to support climate risk analysis and this community. After a bit more of an overview, we will move into the technical portion of our agenda, which will be led by Lou and James. For now, I'm going to turn it over to our first poll, and then Jeff will take. So how many of you are performing climate risk analysis today? Are you just here to learn or just starting to get interested in it? Or are you exploring risk analysis workflows? Could you use some additional help? Or you have already incorporated risk analysis within your common workflows, or it's in an operational? We look forward to hearing from you.
Well, greetings, and thank you for participating in that poll. As Lorraine mentioned, I'm Jeff Donzie. I lead our weather and climate community of interest in Esri. And one of our goals at Esri in developing capabilities to support our understanding of climate is in fostering the development of a community. And as you can see from the list of sectors on this slide, many of them utilize Esri products and services to support their work in understanding impacts of climate change in their various missions, as Lorraine outlined many examples. We see our role as providing a bridge between the producers of climate data and analytics and our many users across these diverse and wide range of sectors. For example, organizations like NOAA and NASA and others are providing access to their really extensive array of climate information products that are derived from satellites, ocean observation platforms, and in situ sensors, into making them available as GIS-ready web services. These services are then available to be accessed by ArcGIS users who will integrate their own mission data to better visualize and analyze impacts of climate in these many areas of societal interests. Esri's own organizational structure provides us the ability to assist in that connection. As you can see here, our teams are aligned to many sectors, from utilities to public safety to the insurance sector, to name a few, to ensure the information and tools they need to support their use cases. And with increasing demands to evaluate climate risk and really the volumes of data and information, Esri is working to increase the capabilities in our software and services to support these requirements. Among them, these additional capabilities are incorporating AI and machine learning, better big data management, real-time sensor observation monitoring, and service enabling dissemination of web maps and services in the cloud, all of which are going to be increasingly important to many of you in the years ahead. Another important part of the Esri weather and climate community is our extensive Esri Partner network that have a deep commitment to helping further develop and support the ArcGIS platform. A growing number are using our technology to incorporate climate risk analytics in their products and services. The partner network actually has over 3,500 organizations across many categories, including solutions, services, content, and systems integration. A few of them sort of listed here in this montage. We have a number of startups in our emerging business program too that are on their way to becoming full partners, several of which have a focus on weather and climate. You can go to our website to see more about our partner community as well. Another community resource that's pretty amazing to be aware of, if you're not already, is the ArcGIS Living Atlas of the World. It's maybe the foremost collection of global geographic content, including specific resources for oceans and the atmosphere. It includes thousands of data sets in GIS-ready format, maps, apps, but also authoritative sources from thousands of contributors, such as in this sector, National Weather Service, NASA, USGS, the European Environment Agency, and others. In the Living Atlas, we have a series of core services and apps that help companies monitor severe weather events, changing patterns in climate, that in turn help them to assess, detect, predict, and quantify the impact of climate change on their business. We'd welcome additional data to be contributed by your organizations if you feel those can benefit others. That's the whole concept of the Living Atlas, is a community resource. I would also like to point out a recent release we've made, the team has made, of the Esri Climate Hub. The Climate Hub includes links to data, story maps, and other content of interest to the climate community. We encourage you to take a look at the hub. There's a form in the hub inviting contributions too. And in fact, you can use the hub application framework to develop your own hubs to serve your user communities. The link to the site you'll see is provided at the bottom of the slide and in the resources slide at the close of the webinar. In the hub, you'll find best practices for applying Esri technology for climate analysis, including contributions from some of Esri's partners in the climate domain. You'll also find several sample applications that may give you ideas for your own work. But now, to show you how to go through the process of working with climate data and to develop analytical workflows, I'm going to turn it over to Lou. Lou?
Jeff, can you see my screen?
Yes.
Okay, thank you. So I'm going to quickly show you a demo to kind of show weather and climate risk at a local level. Today we're going to be focusing on the effects of heat island. If you don't know about the heat island effect, its areas in the city tend to be warmer than its surrounding suburbs due to the artificial surfaces that absorb heat a little bit quicker, such as asphalt and other types of pavements. This could be problematic for many cities around the world this summer, including our study area of Washington, D.C. So I'm currently in a ArcGIS Pro 2.6 environment. It's our desktop GIS client, and I have this raster surface of DC air temperature. Taking a look at this raster, you can kind of see that areas over parks, as well as areas closer to rivers and other bodies of water, tend to be a little bit cooler. So we'll follow the typical scientific ArcGIS workflow. We'll start with some raw data sets such as this that are stored locally, but also access some web services stored in the cloud. And we'll end with the final layer that represents which neighborhoods are being the most impacted by the urban heat island effects this summer. We can then enrich this data with population profile, as well as predictors to determine which factors result in the urban heat island effect. In the meantime, we'll also have a discussion on replicating your workflow using Python. So if you're familiar with Python, we can incorporate some common libraries to manipulate your GIS data. And lastly, we'll conclude by evaluating a model for predictors of the heat island effect. So with that being said, here is our raster. And the first thing we want to do to evaluate the urban heat island effect is to set our raster extent. So the first tool we'll be running is the raster domain tool. And this tool is going to intake our raster and get an output feature class consisting of the extent of our study area through a polygon. So here is our study area. And from the study area, we now need to extrude some neighborhoods where we can now measure the impact. And a great way to get these neighborhoods is through the Living Atlas, which Jeff mentioned earlier. So by using data that's published by the US Census Bureau, I can go ahead and go to the Living Atlas, get this URL endpoint, and go ahead and add this straight into my GIS environment. So after doing a spatial query, I can now get the census tract that completely are within my study area for me to calculate the average temperature by. So next, I can now run this tool called Zonal Statistics as a table. So if you ever used SQL before, think of this as a group by, but you're summarizing it by the polygon level. So in this case, I'm going to pass in my census tract layer, and I'm going to summarize the average temperature for each and one of these neighborhoods as defined by the US Census Bureau. And by doing so, I can go ahead and get the average temperature for each and one of these areas, as well as calculate the anomaly from the mean for the whole study area. So if I take a look at this results, it's not surprising that the central, most densely part of DC has the highest temperature. And if you take a look at the legend, these areas can be up to 4 degrees Fahrenheit warmer than the average temperature, and even up to 7 degrees difference compared to its surrounding parks. So with that being said, you might be wondering, is the heat island effect statistically significant in this case? And what I mean by that is, are these values out of normal pattern, or out of is this a real pattern, or just or something more random? And to quantify this and evaluate this in a statistical manner, we can go ahead and run the evaluate hotspot analysis tool. So by running this tool, I can point towards my air temperature anomaly data and choose the average temperature as the field to evaluate. And the output result of this tool tells me that these areas over central DC has a 99% confidence level that these areas are indeed statistically significant, and these higher temperature are not due to just a random distribution. And furthermore, to its neighbor, the corresponding park has a lower than average temperature, and this is statistically negative as well. So with that being said, you can kind of evaluate the effects of the urban heat island effect for the city of Washington, DC. But since this will be a phenomenon that affects all cities for the Northern Hemisphere this summer, you might be, how do you replicate this for all cities within the world? One option you can go with is using our Python offerings. Our ArcGIS Pro desktop client, it's a really good analytics workbench. It includes a built-in Python notebook. So I can replicate the workflow I just conducted, that I just showed you, using a Python environment, so you can replicate this workflow for all cities in the world. So by using the ArcGIS API for Python to read in online services, such as the US Census Bureau of neighborhood data, and ArcPy to compute some local analysis, I can go ahead and use ArcPy to, again, filter and get my raster extent. I can use the ArcGIS API for Python to go ahead and get that census layer that's stored within my living atlas. So I'm using completely hosted data, nothing that's written to my disk. So then I can go ahead and get the extent of my raster as a polygon and do a spatial query from that census layer for all census neighborhoods that are within my polygon extent. Using the ArcPy function, I can now run the ArcGIS zonal statistics tool to calculate the average temperature for each specific census tract. And using the built-in pandas data frame that's built directly within the ArcGIS API for Python, I can go ahead and read in my tract data as a feature class as a pandas data frame, and go ahead and join that with the average temperature, which is also stored as a data frame. And by using pandas, right, which is a common library for analytic workflows, I can now create new fields to my geographic data, such as converting my temperature from Celsius to Fahrenheit. As you can see, this is a lot easier than working with the cursor and ArcPy. And from here, I can also add in additional fields, such as anomaly from the mean. So after I've done all of my hard work, I can go ahead and export this out as a service, or in this case, as a shapefile for further analysis and storage. So with that being said, you just kind of saw how the most impacted neighborhoods within Washington, DC, with regards to the urban heat island effect. Let's take a look at which factors lead to the urban heat island effect. So we'll do a little bit of data engineering before we get a taste of modeling in an ArcGIS environment. So again, here is that data set that we concluded from before. You can kind of see the anomalies from the mean. Now we want to enrich this data set with additional predictors. And the predictors that we're going to get are directly from various data sets that are published by various agencies. One predictor that we mentioned earlier that might lead to the urban heat island effect is NDVI, which gives you a general indication of vegetation for a specific area. So by using the living atlas again, I can go ahead and extract this USDA NAPE layer, which gives me a general indicator of NDVI values across the US. Furthermore, I can use the living atlas to extract other layers, such as land cover, because I'm hypothesizing that the proximity to water sources might be another predictor to the severity of the urban heat island effect. So I can go ahead and extract both of these data sets and add it into my ArcGIS Pro and go ahead and run zonal statistics to get the general distance from water, as well as the average NDVI for each and one of these neighborhood census tracts. Furthermore, I'm gonna add in 2 more variables as predictors to my data set. And a fast way to add in additional predictors is to use the enrich tool. And the enrich tool allows me to add in additional demographic variables to each and one of these features as a new column. So in this case, I added population density, which might be related to urban heat island effect, as well as the population that takes public transportation. If I wanted to add in additional variables, I can certainly do so. Esri, working with our partners, we have incorporated hundreds of different variables across all demographic variables that you can incorporate and engineer directly into your data set. So by running these tools, I now have a complete data set. And if I go ahead and inspect the attribute table, you'll notice that my new data is directly added as columns in my data set. So with that being said, let's go ahead and move on to the modeling component now, because now I have my predictors ready. But before running the model, we might need to normalize our data. So we want to normalize our data to the same magnitude. So we'll go ahead and run another data engineering tool called standardized field. So this is going to transform all of my predictor variables as well as response to the same magnitude on a range from 0 to 10. By doing this, it's going to allow me to interpret my model outputs a lot easier. And this is just one tool that's part of Esri's data engineering toolbox that allows you to encode your field, reclassify your field, and transform your data to a normal distribution. So once my data has been normalized, I can now start running models. First model I want to try out, and the only model I want to try out for today, is the generalized linear regression model. So from here, I can go ahead and point towards my training data. I can choose my predictor, as well as the link function that I want to use. So if I want to predict the continuous, I'll use the ordinary least squares, but you can also predict to logistic or a rate using Poisson. Now I can input my explanatory variables. So in this case, I'm going to point towards the distance to water transformed, population density, percentage that uses public transportation, as well as the average NDVI values for this area. And by running the model, I can go ahead and run this model and take a look at the results. Now, before I take a look at the results on a model, before I take a look at the results on a map, I can take a look at the model metrics first. And to take a look at the model metrics, I'm going to view the details and expand the logs, more specifically the environments. And contained in the messages contains all the model metrics that allows me to run a statistical inference on the model. So first, I want to point you towards the coefficients. So these coefficients determines the relationship between the 4 predictors and the average temperature for that neighborhood. So not surprisingly, the higher the NDVI value, the lower the temperature. And this inverse relationship is captured by this negative coefficient. Some other observations I observed through the model outputs is the distance to water, which is positively, which is represented by this positive coefficients. And this indicates that holding for all these other variables that the closer the distance to the water, the lower the temperature it's going to be. Furthermore, you can get the p-value to determine whether these observations are statistically significant, as well as the VIF value, where my cursor is, to determine that multicollinearity is not present in my model, and these 4 predictors are not redundant in one another. Lastly, I can point you to this R-square value of 0.66, which means that we have created initially a decent model in that our data explains around 66% of the variance found within our data set. So with that being said, let's take a look at our model results on a map. And this is where our model starts falling apart, where the wheels start coming off. Because as you can see from the legend, our residuals are clustered together. And this violates one of the assumptions of linear regression. And our diagnosis, this could indicate that there might be additional factors that determine temperature that we didn't include in our initial model. And by taking a look at this, this really highlights the benefit of running it on an ArcGIS environment, because it could detect these spatial patterns, such as these clusters of residuals. And say if you ran this in our environment, you couldn't necessarily get this plot, right? You would necessarily visualize the standardized residuals on a scatter plot, which we also provide as well. And you'll see that the residuals are normally distributed or randomly distributed, which in this case, they're not spatially. So this really highlights the exploratory nature of modeling. If this is something you're interested in, we provide extensive tools, various modeling algorithms for you to use. What I just showed you just scratches the surface of your models. And if this is not enough, as you saw in earlier integration concepts with Python or even R, you can bridge your GIS data into a Python environment or R environment to run your own models. So you just saw using GIS tools with local hosted data provided by various agencies, we're able to evaluate not just which areas are impacted by the urban heat island effect, but also take it a step further by trying to explain why this may be the case. And we can go ahead and share our layers to an ArcGIS online environment so that the general public or my colleagues can also view my results and expand further on my analysis, as well as take action. So with that being said, I'm going to go ahead and pass over to my colleague James, who's going to show you his demo.
Thanks, Lou. Okay, and just let me know you can see my screen. There's a white slide with a white background. Great, thank you. So that was some really cool stuff that Lou was working through, and I think it shows a lot of the capabilities that we have within the ArcGIS ecosystem and using Pro as the main engine. And there's a lot of different data types when it comes to climate and weather and atmospheric science out there. And scientific data, it really comes in many shapes and sizes. But often when we talk about scientific data, we're talking about data that represents geophysical, environmental, climatological, or atmospheric phenomena that occur over space, which can be two-dimensional, time, adding another dimension, and or at height or depth, so two more dimensions. So say sea surface, sea temperature at depth, sea salinity at depth, air temperature at height. Because of the multidimensional aspect of the data, you may have heard of this described as a data cube or an image cube. In the end, it's what we call a multidimensional raster within ArcGIS, and commonly used data types such as NetCDF, GRIB, HDF can be managed and disseminated and analyzed without changing the source data within ArcGIS. With what we call an image cube, we can produce an operational picture that can be queried to extract patterns and trends that can help shape decisions about specific areas of climate risk. And this data comes from a whole variety of sources. A good example of this, which I'll be using in just a few moments, is daymet temperature and precipitation data, which can be fed seamlessly into the ArcGIS data model, and it can be managed, analyzed, and visualized with a whole host of built-in capabilities within the platform. These data sources can have a highly variable velocity, and they can be monthly, daily, or even hourly measurements. And another example of this could be data coming in at a daily rate from the physical science laboratory within NOAA. And this data can be added in very quickly and without the users, without much hands-on manipulation from the user. And it can be fed, a system such as this one could be created where cloud-hosted data is updated nightly into a mosaic. That image cube is created and managed within a geodatabase. And the tools within the ArcGIS ecosystem allow the data to be disseminated, to be analysis applied and disseminated to a whole host of different applications, whether it's an ArcGIS web application, an ArcGIS notebook, or ArcGIS Pro like Lou was showing. This wealth of data can be used to inform policy decisions as users tackle a whole host of different problems. And one of the ones that I'm going to be discussing today is the effects of our changing climate on agricultural health in the Western United States. With dense data sets such as like daymet temperature, something like growing degree day calculation can be measured for specific crops. If you're not familiar with the concept of growing degree days as a way to measure the variability of certain crops, you could think of it as a tool to measure the viability at certain temperature thresholds of specific crops and how many viable days they have to be productive. With the built-in tools available in ArcGIS, we can define thresholds within the data and allow us to assess risk to certain specific agricultural industries. And really understanding something like growing degree days or other climate indicators really lets us understand how climate change will affect day-to-day life. And as working through a problem like this with assessing agricultural health for specific industries over a certain geographic region, often the work begins with something like this: scouring the internet for different data sources, finding something like daymet, exploring how to access the data, and then feeding it into something like an ArcGIS notebook where I can create a request to the thread server. I can download the data locally, and then I can start feeding it into ArcGIS. I can create a mosaic data set directly out of those NetCDF files that have been downloaded. I can quickly visualize that either within ArcGIS Pro or a notebook. And then I can start using some of these built-in tools to access the variable information, whether it's temperature, so I can quickly view the number of measurements within my data set. I can view the maximum measured temperature, the minimum measured temperature, and then I can subset the data into two different variables with temperature and maximum temperature and minimum temperature. I can then aggregate that data with built-in tools and apply different temperature thresholds to create a scenario where I can add values to the maximum and minimum temperature and define a threshold for a certain crop, such as strawberries in California. I can process that data, that subset of data, and then I can categorize that data into different regions within my area of interest. I can remap those values into different viability zones and to create a suitability index. And then I can view the metrics of that suitability index across different regions. I can summarize the suitability of certain regions with that growing degree day estimation, and then I can quickly plot them within the notebook using the capabilities from Panda's data frame. From here, I can view side-by-side analysis with different temperature thresholds for different crops. And I can quickly see on the left more variability in growing degree estimation as I increase temperature. From here, I can then share these results to ArcGIS Online with the new ArcGIS capabilities to host imagery as well as analyze imagery built into ArcGIS Online. Since the data has been shared to the web, I can quickly create a configurable web application so other users within my organization or the public can interact with my findings. I can use built-in widgets to display different climate scenarios for something like strawberry crops or barley. I can allow users to interact with these two different scenarios, one with a +1 growing degree day and +2 growing degree day. I can play out these scenarios with these time-enabled layers and view the changes that could take place. Or I can allow users to enter in to enhance the enhance the application with their own data. Say I own several strawberry farms in Northern California. I can add data, my own GIS data, to the application. And then I can pinpoint which of the locations of my farms have the greatest effect from more temperature variability during the growing season. So I've shown you here a way to find data, extract it, use the built-in tools in ArcGIS to not only manage the data, catalog it, but analyze it and visualize it very quickly, all representing an end-to-end workflow to be able to use all the built-in tools within ArcGIS to create a quick climate risk assessment to show how all of this data coming in can be leveraged and used on a daily basis. And with that, I think we'll have another poll question.
Yeah, so we're curious to know about what type of risk analysis or just climate analysis workflows what tools you are using. Are you using notebooks, Python, R, ArcGIS, or other? So I hope you enjoyed those demos, getting really technical and really just showing the depth and breadth of analysis capabilities on how to assess climate risk within the ArcGIS platform. You saw how ArcGIS could seamlessly connect to a variety of data sources, removing the burden to learning how to connect to different types of cloud stores. For those comfortable in the scripting environment, we hope that you enjoyed the demonstrations on using Python notebooks, and to see how it makes it easy to integrate GIS into common climate risk applications. Again, we put these 3 webinars coming up in this series. We hope that you'll have the opportunity to join us. We're going to, let's see, now open it up to questions. And a bunch of them have been accumulating in the chat. With respect to the last poll question, we can see that about more than half of the folks attending the webinar today are already using ArcGIS. That is wonderful to see. And we can see that there's a healthy percentage of folks using both Python and R. So you got to see quite a bit of that in today's session. We had some questions about, there are about 58% or so wanted to learn more about climate risk analysis and had asked if we had training resources. And so, as I said earlier in the presentation, we'll be sending an email with a whole series of links to resources to help you further understand and practice how to do risk analysis using this platform. So those links will be provided to you. There's another one, are there tutorials available to become more familiar with these tools? And yes, I just answered that. So again, all of these links will be provided to you. And so some of the notebooks that were presented today, we've had quite a few users. Over to Lou and Jane. Will these notebooks that you had shared with during your analysis, will they be made available for the users?
Hey, this is Lou. I can definitely share my notebook that I showed in my demo. You're going to have to, since it requires the web services that's available to everyone, I don't think you have to bring in your own data sets. We'll definitely make that available.
That's great, Lou. And we'll include a link to the notebook in the resources that we provide out to everybody who has attended. Here's another question that could probably be addressed by both Lou and James. How is the GIS community taking advantage of the IoT platforms and cloud-based computation of data science algorithms? I mean, we just saw some of this now, but in particular, they're looking at near real-term information. So bringing that in and dealing with that in your analysis. Could either of you speak to that?
Yeah, so I think this speaks to kind of a growing need throughout the atmospheric science community as well as the climate science community, is bringing in these data sources almost as they're measured and visualizing. And there's a whole host of tools within ArcGIS to do that. And I showed what is basically daily interpolated measurements, but these daily measurements can be fed in hourly or even through the measured at the minute, can be fed in through a real-time system in ArcGIS. So there's 2 different ways that can be done, and it can all be added to a data set that's updated seamlessly to the users. As that's happening, distributed processing can take place, so further analytics can take place. And these are tools that are built into, some of them are built in already to ArcGIS Online. They're all available through some of our enterprise level software. So think about GeoEvent server as well as geoanalytics to process data at scale, and then image server, which can distribute the processing of pixel data at scale. More of these capabilities are being added into ArcGIS Online, so the real-time capabilities of Velocity in ArcGIS Online as a service, as well as the new imagery capabilities where raster data can be processed as it's pushed into ArcGIS Online.
Thank you. And also, we mentioned earlier that we have a Climate Hub that has all kinds of resources and training and links that could assist you as well to get more familiar with some of the concepts that we presented today. And if you think the applications and use cases that I talked about earlier on in the presentation, we have links to all of those in a little bit more detail so that you can learn a little bit more about those. Lou, this question is for you about heat islands. Have you tried doing your analysis for all cities in the world? And if so, did you run into any computation limitations?
Hey, that's a good question. I have not done it for all cities in the world, only for Washington, D.C. But as far as my experience, I would say it's certainly possible, and it wouldn't take too much extra effort to replicate this for other cities. Like James mentioned, many of our tools are built with options to invoke parallel processing, so using all of your cores on your machine to spread out the analysis. So that really speeds up the workflow, and and the same concepts applies for many of the services-based tools that James and I showed using the ArcGIS API for Python as well. So it's definitely scalable across different regions too.
Thanks, Lou. Another question for you is, what source of the temperature data did you use for the hotspot analysis?
Sure, this is a data set that's provided by NOAA. I can send the exact link to the data in the resources page, but the way that the data was derived was a mix of ground truth data, and that's being interpolated with remote sense data, more specifically Sentinel data, which measures the ground temperature, and that's being translated to air temperature.
Okay. We have another question, and I think pretty much Lou or James could answer this. Most of the data sources used in the modeling presented today are for the US. Are there data for other parts of the world?
So there is, and I think this is a good question because I've work a fair bit on climate and climate impacts on agriculture in places like Eastern Africa and Australia. And so one place to leverage, one place to look at to leverage data is the Copernicus ecosystem through the European Space Agency. There's a whole host of daily and monthly and aggregated content through Copernicus that can be downloaded and analyzed. Some of the work that Esri is doing with the Living Atlas heavily leverages that data. And I would also look at other US data sources like MODIS that can be accessed and downloaded.
Thanks. We're also getting quite a few questions about, do we have step-by-step instructions to do the urban heat analysis that was just presented?
Yeah, sure. We'll be making sure to send the resources, the notebooks, which documents the steps, as well as I might also include the tools that we use to arrive at those steps, including field calculation, zonal statistics, and raster extent. So look for the resources for a more detailed step-by-step way to do these analysis.
Yes, Jeff, I might just add, Lorraine, that through the Climate Hub and some of our Weather and Climate site, we also have some blogs on some other examples of end-to-end working with climate data. So I think, as you mentioned, we're going to be providing links to those resources.
Yes, that's correct, Jeff. We'll be providing links to that. There's quite a bit of information that we will be supplying to you that could really beef up your knowledge and skills. Let's see. Questions about, will the presentation be shared? We will have the webinar shared, a link to it. It will go on our website, so you always have access to be able to view this again. And then, of course, you can always reach out to us if you need additional information over and above the resources that we will be supplying. And I think that's about it for questions. Most of the other ones are to do with training. There's a lot of interest, perhaps because we had about 58% want to learn more about climate risk analysis. That's wonderful, and you're going to be excited about the list of resources that we will supply to you after the webinar is concluded, so that you, excuse me, can continue to learn. So we'd like to thank you, and we welcome additional feedback at sciences@esri.com. Feel free to reach out to us. We're always open to hearing anything that you have. We hope that you found today's session informative, and we invite you, like I said earlier, to attend additional webinars. So today, this will conclude our webinar broadcast. Thank you so much for joining.